As the world advances, engineers are tasked with challenges and problems to further develop and push forward what we can achieve. This semester, our team was tasked with building a prototype to demonstrate resource extraction on a mock lunar surface. This prototype had to do certain functions. Firstly, it had to be able to move around the lunar surface, traversing different terrain. Secondly, the robot had to be able to collect samples from in the open and under rocks. Thirdly, it had to be able to identify each separate object. And finally, be able to navigate its way around a surface. Each team member was assigned one of these subsystems. Now, for this demonstration, the robot had to fit within a 1.5U form factor and autonomously move around a mock lunar surface, collecting samples simulated by golf balls from in the open and covered by rocks to then return them to the lander for scientific analysis. Hi, I'm Alex and I've been tasked with developing the mobility system. For this prototype, the mobility system had to be able to move the robot around the mock lunar surface quickly and smoothly while giving enough precision to collect samples. Now to do this, a differential drive system was chosen for its simplicity and robustness. Then a track system with a 210-to-1 geared electric motor to drive each side was used. This provided sufficient grip with enough speed and torque to effectively traverse the different slopes and angles on the lunar surface. These motors were then powered through an L298N dual motor driver, which was fed by a 7.4-volt lithium-ion battery. This allowed the Raspberry Pi to send a PWM signal to the motor driver to then adjust and determine the motor speeds. This mobility system was then encased in a laser-cut acrylic chassis that has been developed to integrate all the subsystems into a small, functional, aesthetic package that could be serviced easily.
My name is Matthew Whitfield, and I was responsible for the collection system. We decided on a tubular design for the sample collector, which was positioned at the front of the robot, below the Raspberry Pi camera. The robot was programmed to navigate over the sample and activate the collection system protocols. This would force the collection system downwards over the ball using a nut and threaded rod system. A rubber flange provided a pseudo barrier that the sample was able to move through when enough vertical force was placed on it. The collector module was raised to a halfway position once the sample had been obtained, which allowed for the robot to move freely with the captured sample. The position of the collector system was determined using a series of microswitches at varying heights which would return a state variable to assist with the AI module. Once the prototype had mounted the lunar lander, the collector module was then raised to a maximum height, which provided a downward force on the ball, dropping it into the lander.
Hi, my name's Dwayne. I was in charge of the vision subsystem.
Because our robot was required to be autonomous, we needed a way to tell our robot what to look for. To do this, I used the HSV color space to segment out the different color objects that would need to be detected in the field. Luckily for us, the sample, rock, obstacles, and lander were greatly different colors, so there was no issue thresholding them separately. To give the navigation something to work with, I used an equation to find the distance to an object based on its pixel size within the image. I was also able to find the bearing by finding the distance between the centroid of a blob and the center of the image, and map that value to a positive or negative angle based on the horizontal field of view.
Our robot needed a way to autonomously interact with the world around it, and so it took information from the vision system, such as the classification and range of objects around it, and then intelligently made decisions about what the next action should be. Whenever a target is seen, the robot will attempt to drive straight toward it, and if the robot loses sight of it for any reason, it will remember if the target was on the left or the right, and the robot will rotate in that direction to regain visual contact. It would navigate around the obstacle by driving straight toward it and then taking an algorithm of steps designed to circumnavigate the obstacle. If this algorithm does lose sight of the sample, the robot will know how to rotate to regain sight of it. When the robot successfully navigates nearby the target, it will aim straight to the target and reverse or drive forward so that way the target is at a predetermined distance from the robot before attempting the appropriate procedure to pick it up. The robot will next rotate again to the lander, approach it while avoiding the obstacle in the same way, and again drive to a predetermined distance before driving straight up the ramp and executing a deposit onto the lander.
In the end, we got all of the basic functionality for the robot done. Our only letdown was our program still had errors in it which we didn't have time to fix. Thank you all for watching Team 5's robot video. We'll see you all on the next frontier.